Hi, this is a video where we are going to be covering sections 13.4 to 13.6 in Zumdahl. This is going to be looking at equilibrium and some of the calculations that we do with equilibrium. First thing is just to talk about the difference between heterogeneous versus homogeneous equilibria. These are our homogeneous equilibria. These are all in the same state or phase. We would include all of these when we write the equilibrium expression and if we were going to do any calculations. Heterogeneous equilibrium have more than one phase. So in here you can see that we have a solid, another solid, and a gas. So the position of the equilibrium, so the equilibrium constant, doesn't include things that are solid or liquid because they don't really have a molarity that can change. They don't have a concentration. So if I were to write the equilibrium expression, it would be equal to, essentially these are constant. It would just be the molarity of the carbon dioxide. Similarly, if I was going to do the KP, the pressure equilibrium, I would do the partial pressure of just the CO2. In this slide, and you can follow along in Schoology, this just kind of derives and shows that if we were to include them, they would be constant and they come out of the expression. So here's some examples. You could definitely try these and then pause the video and then see. So for this first one, if I were going to write the equilibrium expression, in terms of concentration, I'm going to exclude these solids and it would just be the oxygen. I could do Kp also, would be the pressure of the oxygen cubed. Here we're going to remove the liquid. Our equilibrium is only dependent on the hydrogen and the oxygen. My Kp would be the pressure of the hydrogen squared times the pressure of the O2. I think I'm going to skip these. So applications of the equilibrium constant. So the reason we calculate is because we want to know the value of K. And if we have a large K value, that means that we're going to mostly have products. We say that the equilibrium lies to the right or it favors the products. The reaction essentially goes to completion. The larger the K, the more you can say that. A small k means that the equilibrium lies or favors the left, or the reactants are mostly going to be present. This is a reaction that really doesn't occur to any significant extent. Just so you know, the value of the equilibrium constant is not related at all to the rate laws and the rate constant. So just keep that in mind, that the K is similar, but the equilibrium constant, capital K, is just telling us the extent whether we're going to have more products or more reactants, not how fast the reaction will occur. We have something called the reaction quotient. This is Q. We write it exactly how we do the equilibrium expressions in terms of concentration with the law of mass action. So it's still going to be the products raised to the power of their coefficients over the reactants raised to the power of their coefficients. The difference is that these are going to be initial concentrations. And then we're going to use this value to decide whether or not the reaction we're talking about is in equilibrium, or if not, which way is it going to have to shift in order to get to equilibrium. Once we have the value of K, and I'll show you how to do this soon, if it equals K, then we can assume the system is already at equilibrium. If Q is greater, that means there's too many products, so the reaction will shift to the left until equilibrium is established. And then if Q is less than K, that means that there's too many reactants, not enough products, so it will shift to the right to reach equilibrium. Okay, so let's do this problem together. So this is the synthesis of ammonia from the elements. These are all gases. So if I were to write the reaction quotient, Q, it's going to equal the initial molarity of the ammonia squared over the molarity of the nitrogen times the molarity of the hydrogen cubed. These are all initial. You don't have to put the zero or the sub naught there if you don't want to. So then let's plug in. So in this question, they're telling us the ammonia molarity. And we're going to square that over the nitrogen. And then the hydrogen value here. And that one will be cubed. So when I do this calculation, I get a very large Q, 1.3 10 to the 7th. No units, just like K. So, and in the question, they are giving me the equilibrium constant right here. So you can see that Q is much larger than K. That means this reaction will shift to the left to make that the product concentration go down, the reactant concentration go up, which will overall reduce the equilibrium constant and reach, in order to reach equilibrium. Let's do, now we're going to move on to a technique that we can use to solve some of our equilibrium problems. It's called a rice table or an ice table. And I will show you how to use this in the coming problems. So here we have a reaction. And in our first trial, we are going to start with 6 moles per liter or molarity of iron, 10 moles per liter of the thiocyanate ion. And then at equilibrium, the concentration of the iron thiocyanate complex ion is 4. What is the value of the equilibrium constant? So this is where we will try using our rice table. So R is for the reaction. It's helpful to have it right here in the problem. I know it's up above, but I is the initial condition. So in the question, they said we start with 6 moles per liter. This always has to be molarity, by the way. So if you're given moles and the volume, you do have to calculate it. 10 moles per liter of the thiocyanate. They don't mention the iron thiocyanate at the beginning, so we're always going to assume that's 0. C is for change, and we will deal with that in a second. And E is for equilibrium. So in the question, they're telling us that the equilibrium concentration of the iron thiocyanate is 4.0. That means this is 4 molarity at the end once it reaches equilibrium. That means this is change. So that means I had to have made 4 moles per liter of the iron thiocyanate complex. Then I can figure out the change in the iron plus 3 by taking the 4 molarity of the iron thiocyanate, and I'm going to do a mole ratio. There's 1 mole of iron 3 for every 1 mole of the iron thiocyanate ion. So you can see that I am going to get an answer of 4. So this is going to be used up because I'm producing, let me show you, sometimes I do this. I am producing the iron thiocyanate because I started out with 0, and then I'm using up these 2, so they're going to be negative. Showing that, you don't need to show that mole ratio on how I got the 4, but I just wanted to teach it to you. So similarly, let me get that out of there. Similarly, again, we can start with this one that we know. I'll do it up here so you have more room. That's how many moles per liter of the iron thiocyanate ion. So I'm going to do a mole, and I know I have 1 mole of thiocyanate for every 1 mole of iron thiocyanate. So the math is pretty easy there. They're in a 1-to-1 ratio. So then what I do to get my 2 equilibrium values here and here is I just add going down. So I'm going to take 6 minus 4, which gives me 2. So at equilibrium, I'm going to have 2 moles per liter of iron plus 3 ions. Similarly, I'm starting with 10 moles per liter. I'm going to use up 4. So I have 6 moles per liter at equilibrium of the thiocyanate ion. In the question, they want to know the value of the equilibrium constant. So now I'm ready to plug in to my equilibrium expression, which is going to be products over the reactants. And now I can just sub in that row. So the row, the whole point of doing this is to get these values. So it's going to be 4 over 2 times 6. And when I do that, I get 0.33 repeating. Remember, no units. So the K for this trial at this temperature is going to be 0.33. Let's do another one. So this is going to be a little bit different, but we're still going to use the Rice table. So in this trial, we're starting with 10 moles per liter of iron, 8 moles per liter of thiocyanate, and we want to know this time the equilibrium concentration of the iron thiocyanate ion. So it's different than the previous question, because in the previous question they gave that to you. We're going to assume it's the same temperature, so we have the same K. So our K is still 0.333 from the previous question. But we're going to use a Rice table again. And my reaction is still the same, but it's helpful to have it all right here. And then my initial amounts have been given. You don't even need to really put units there if you don't want to. Just make sure they're always molarity. They don't give me the iron thiocyanate, so we know that's going to be 0. And then we're kind of stuck. So what we need to do here is think about the change, the C. The change is, it might be helpful to divide this, or at least in your head divide it. So remember, you're going to be making the iron thiocyanate. So we're going to say our change is plus X. We're going to be using up both of these. So they're going to be negative X. And then you still add going down. So at equilibrium, the concentration of the iron plus 3 is 10 minus X. The thiocyanate is 8 minus X. And the iron thiocyanate is X. So these are the values that I'm going to put into my equilibrium expression. So remember, my K is iron thiocyanate ion over the iron plus 3 and the thiocyanate ion. Remember, K is 0.333, and now I can plug in X over 10 minus X times 8 minus X. So this is the point where you get to do the math however you'd like. I'm recommending that you multiply the whole thing by 3, because that will give you 1 equals 3x over 10 minus x, 8 minus x. But then you have to do the math. You do need a FOIL, and you do multiply it by 1, which won't change anything. And then you do need to simplify it. Once you simplify it into the format of the quadratic equation, you should get x squared minus 21x plus 80 equals 0. So my A is 1, my B is negative 21, and my C is 80. And you can get a quadratic formula calculator on the computer or on your calculator. You can program it. But basically, x equals, remember, negative b plus or minus the square root of b squared minus 4ac all over 2a. Is that right? I think it's right. Let me look. Yes. So then I just sub in. So be 21 plus or minus square root 21 squared minus 4 times 1 times 80 all over 2 times 1. And you can do the math here, but I'll just tell you, you're going to get an answer of 16 and 5. So you'll get 2 answers. Sometimes one of them's negative. You know right away that one's not valid. Here, there still is one answer that's accepted and one that isn't. So what we want to do is look back at this. So the concentration of the iron is 10 minus X. So there's no way that it can be the 16 because then we would get a negative molarity. But we can easily sub in the 5. So the molarity at equilibrium of the iron plus 3 is 5 molar. The molarity of the thiocyanate is 8 minus X. I know in the question I think they didn't ask you all these, but sometimes they do. So 8 minus 5. So that'll be 3 molarity. And then the iron thiocyanate is going to be equal to X, which is 5.0. So those are fun. And you will see some of those on the WebAssign. And then let me just show you one other type of problem. This is putting together now Q and our rice table. So in this question, we have, we have our reaction. I'm going to write my reaction is H2 plus I2. They're all gases, so I'm not writing down that they are. And then they're telling me that the equilibrium constant, so they're telling me K. And then they're saying that suppose the HI at 5 ATMs. So actually, yep, this is KP. So the value, they're all mixed together. So we can assume these are the beginning amounts. So we have 0.5 atmospheres. And then the hydrogen, so these are our initial, is 0.01 atmosphere. And the iodine is 0.00500. So this is where, in the previous problem, we would have then just said, minus X or plus X, but we can't be certain right now which one is going to be made and which one's going to be consumed. So what we have to do is calculate Q to decide on what way the reaction is going to shift. You can't assume it's going to go to the left because it's possible it has a really large K value. I mean, it is 1 point, it's 100. So we'll do it. I'll just show you. So in this question, if we were going to write the Q, the reaction quotient, it would be equal to the pressure of the hydrogen, iodide, squared over the pressure of the hydrogen times the pressure of the iodine. So in our beginning, remember, these are always the initials. So technically, this is kind of QP. So our initial partial pressure of the hydrogen iodide is 0.5 squared. And then the hydrogen was 0.01. And the iodine is 0.00500. So when I do that, I get a Q value of 5,000, which is much larger than my K, which is 1.0 10 to the second. So therefore, the reaction is going to shift to the left. So knowing that it's going to shift to the left means I'm going to be making these two and using this one up. And they're all in a, well, they're not all actually. So this would be X, and this would be 2X because of this 2. So then my equilibrium values are going to be 0, 1. I'm just going to not worry about sig figs. This will be 0, 0, 5. Oops, sorry, these are plus X. And then it'll be 0.5 minus 2X. So now I'm ready to plug into the equilibrium expression. And I know my Kp is 1 10 to the second. And that's going to equal my partial pressure of my hydrogen iodide squared over the partial pressure of the hydrogen times the partial pressure of the iodine. So I would sub in 0.5 minus 2x squared over 0.01 plus x, 0.005 plus x. And I would need to get that into the quadratic form, which is, and you can do your math, see if you agree. Whoops, sorry. Sometimes I get these wrong too, and then I have to just kind of start over. So that is what you should get when you simplify. Then you plug into the quadratic. You will get x equals 0.0354 or x equals negative 0.0719. Can't be that one. And then you have to read the question and think about what are they asking. They want the pressure of all the species. So that means the pressure of the hydrogen is going to equal, partial pressure of the hydrogen is 0.01 plus 0.0354, and that is 0.0454. The pressure of the iodine is 0.005 plus x. So remember my x is 0.0354. So I end up with an answer of 0.0404 ATM. And then lastly, remember I'm using these equilibrium expression in my Rice table. The pressure of the hydrogen iodide is going to equal 0.5 minus 2x. And when you do that, you should get 0.429. And you could always plug these back in the equilibrium expression, and you should get a Kp value of 1 times 10 to the second, or close. It might be a little off just because of rounding. I hope that helps. If you have any questions, make sure you ask.